us discuss about the division algorithm using signed magnitude representations. Basically, the computer uses this algorithm to perform a division of any two signed numbers, not a floating point numbers, only signed magnitude represented numbers. Okay, so generally we can calculate with our own hands a division of any number, but the computer has to follow some sequence of steps to perform a division operation. Here the division operation is very easy. It is just a cycle of successive comparisons and shift operations and subtraction operations. Okay, by the binary division is easier when compared to the decimal division is the quotient will contain only two possibilities, either 0 or 1 bit, whereas in a decimal representation we have possible number from 0 to 9. So binary division is easy compared to the decimal division. Long-handed division examples. So here we have to divide 274 with 13. So the 274 we call it as dividend and 13 we call it as divisor. And generally because we cannot calculate directly the 13th 20s, so we only take possible 2 digits or 3 digits based on our knowledge of multiplication table, because I have only 13 table only till 10, so that is why I took only 2 bits. I just consider only 2 bits. So 13 to 26, which the remainder will be 1. So then the next value is copied into the 13 ones 13. So if you subtract these two values, we will get remainder. The value we get here is called quotient and the value we get here is called remainder. The same can be used also for the binary numbers. The 13 equivalent is 1101 and 274's binary equivalent is 1 3 zeros 1 2 zeros 1 0. So 1000, which is lesser than 1101, so we take 5 bits as a first partial product. So 13 ones 13 1101, we subtract these 5 digits with this 4. So generally the subtraction cannot be performed like our normal subtraction. We have to 2's complement this value and add to the 1 3 zeros and 1. We'll get the value 100. 100 is the subtracted value of these two digits. Next 0 will be copied 1000, which is lesser than 1101. So we have to copy another 0 from the dividend. So that is why we keep 0 here and we'll copy the next 0 to the result. Next 1101's 1101. Again we subtract this value, we'll get 11. The subtraction of these two value is 11 and the next bit is 1 is copied to the result. And 111 is much lesser than 1101, so we cannot subtract this value from this. So we'll again add 0, one more 0 and copy the next value to the partial product. Next 1101's 1101. If we subtract these two, we'll get the remainder 1. So all the values of dividend are completed. So this is the remainder. This is called a quotient. The same operation is basically performed using two types. One is division algorithm, non-restoring, and division using restoring algorithm. So let us take the same example. 13 is a divisor, 274 is a dividend. So assume you are a kid, you don't know the 13th table. So 13. So what we'll do, if you don't know, we'll keep on trying for all the digits. First we'll try for a 0. 13 zeros is 0. 27. So which is greater than 13. So quotient cannot be 0. So 0 is not the quotient. So well, let us assume 1 as a quotient. 13 ones are 13. The subtracted value is 14, which is again greater than 13. So 1 is also not a quotient. Next, 13 2s 26. The subtracted value is 1. So which is less than 13. So this we can, if you know the 13th table, you can directly use a quotient as 2. But the computer cannot remember any table, so it keep on trying the values and restoring the value. So this is what the restoring is. 13 zeros 0 will get the remainder subtracted value 27, which is greater than 13. So it will restore. If it is greater, it will restore the 27. 27 is restored, and the 13 will be again checked with the next number. 13 ones 13. The remainder is 14. So it is again greater than 13. So 27 is again restored. 13 twos 26 ones. So till it get the correct value, it keep on using all the digits 0 1 2 3. If it is 9 also, it will be repeated for 9 times. The division algorithm follows these 3 steps. The first step is the divisor is positioned with respect to the dividend and subtraction operation is performed. If the remainder is 0, the answer will be is in quotient. If the remainder is not 0, we'll extend the remainder by adding the next bits from the dividend, and we'll do the same step that we did in the first one. Two types of division algorithms: restoring division and non-restoring division. So this is a circuit required for binary division. It contains registers A and register Q and register M. So dividend is present in the register Q and divisor will be present in register M. So we have n plus 1 bit adder for adding register A to register M. We have a control sequencer which tells the n bit adder to either add or subtract the value of M to the A value, and it is going to set the least significant bit of a dividend. Let us discuss how this algorithm performs. Circular implementation follows the 3 operations that we have discussed earlier. So the divisor will be subtracted from the dividend, and if that result is 0 or a positive, we take the quotient as a 1. If the divisor is a negative, we take the quotient as 0. And if the quotient is 0, the dividend is restored by adding back the divisor, and the divisor is repositioned for another subtraction. This is called restoring division algorithm. Of division operation using restoring algorithm. So initially we have n bit divisor loaded into the register M. Register M contains divisor and register Q contains dividend, and we have a register A which is initially set to 0. So A contains all zeros, and we have n bit quotient because the number of bits on dividend is n, so which is n, so that loop has to be executed for n times. And in this ongoing process, we subtract the divisor from the dividend based on 2's complement arithmetic. Use extra bit position at the left end of both A and M, which contains sign bit during the subtraction. So that is why in the circuit we have n plus 1 bit adder instead of n bit adder. This entire restoring division algorithm follows 3 steps. The first step is shifting register A and Q left 1 bit position. So this is the first step, shift left A and Q. So what is the second step? Subtract M from A and place the answer in A. So a value is assigned with subtraction of a minus m. And so after subtracting the divisor from a, we have to check whether result is negative, positive or equal to 0. So that is known through the nth bit of a. So what is the nth bit of a? We have to decide if nth bit of a is 1 means negative value, we have to take the quotient as 0 and we have to restore the value of a by adding divisor to the a. If nth bit is 0 means that result is positive, we have to take the quotient as 1. So one loop is completed. We have to decrement the n value by 1 and check the value of n. Is n equal to 0? If it is 0, we have to stop the process, and if it is not 0, we have to again shift left AQ and we perform all these operations and check the value of n. After n reached 0, we contains quotient value in Q and remainder in A, and we have to stop. Restoring division algorithm. So input is 11 by 3, divisor is 3. So that's the equivalent value in 5 bits is 0 0 0 1 1, and a dividend we have 11. 11's equivalent is 0 1 0 1 1. And what is the first step? We have to take a as all zeros because we have taken n number of bits as 5. So a contains 5 zeros and n is the number of bits. So contains dividend 0 1 0 1 1, 0 1 0 1 1, and a contains all 5 zeros. So shift left of a and q. So we have shift lefted each bit of a and q towards left. 0 0 0 0 0 0 0. Every bit of q and a are shifted towards left. And what to keep in least significant bit of q, that is not known. So position. So next step is we have to subtract a with m. For subtraction of a is all zeros. So what is m here? M is 0 0 0 1 1. Minus m is 2's complement of m, 1 1 1 0 1. So this 2's complement value has to be added to 0, 1 1 1 0 1. Now add these two values, 1 0 1 1 1. So what now the value a minus m value is 1 1 1 0 1. So this is a negative value because we have 1 here. A of nth bit position value is 1. If it is 1, we have to use q naught as 0. So because this is 1, we have to place least significant bit of q as 0. 0 is placed here. So because this is 1, I used 0 bit, and we have to restore a. So what is a before this operation? A is 0 5 zeros. So that is restored. So one step is completed. We have decremented a value of n. Initially n is 5, now it became 4. And we left shifted each bit position towards left. So next step is we have to subtract a from m. A value is this one and minus m is this one. This has to be added. 1 1 0 1 is added with this one. 1 1 1 0, 1 here, 0 here. 1 0 plus 0 plus 1 1, 0 plus 1 is 1, 0 plus 1 is 1. Now nth bit at a is 1. If it is 1, we have to use the q naught as 0. So because this is 1, we have to use this as 0 and restore the a. So 0, and we have to restore. What is the previous value? 4 zeros and 1, that is restored. Instead of using this a value, we are using back the original value 0 0 0 0 1, and q value is the same thing. This is copied here. Next we have to decrement the n value. 4 is decremented to 3. 3 is not 0, so we have to repeat the loop and shift left AQ. All the bits are shifted towards left. and we don't know what is q naught value. Again subtract a from a minus m. So minus m value is 11101. 11101 is added to this. So we'll get 0 plus 1, 1, 1 plus 0, 1, 0 plus 1, 1, 0 plus 1, 1, 0 plus 1, 1. n value is 1. So we have to use q naught as 0 and restore the value. What is the previous value? 0, 0, 0, 1, 0. That is restored. And this is copied here. Next decrement the n value. N value is decremented to 2. And shift left a and q. We have shift lefted each bit position left. We don't know what is qn. Now add minus m value to a. 11101. 1 plus 1, 1 here, 0 here. 0 plus 0 plus 1 is 1. 1 plus 1, 1, 0. 0 plus 1 plus 1 is 1, 0. 0 here, 1 here. 1 plus 1, 0, 1. This carry is neglected. And what is a of n value? A of n value is 0. If a of n value is 0, q naught is 1. So this makes this 0. Because this is a 0, we have to use q naught as a 1. So then decrement the value of n, that is to 1, and repeat. Shift left aq. We have shift lefted aq. We don't know what is the qn value. Now add a with subtract a from m from a. So we are adding minus m to a. 1 1 1 0 1 is added. 1 plus 1, 0 1, 0 here, 1 here. 1 plus 0 plus 0 plus 1 is 1. 1 plus 1, 1 0, 0 here, 1 here. 1 plus 1, 0 1. 1 plus 1, 0 1. So because a of n value is 0, if a of n value is 0, we have to use q naught as 1. It is 0, we have to use 1. And decrement the value of n. N value is now 0. We have to stop doing. So quotient is in q, which is 0 0 0 1 1, and remainder is in a, which is 0 0 0 1 0. The decimal equivalent of quotient is 3. Decimal equivalent of remainder is 2. So if we divide 11 with 3, we will get 3 is 9 and the remainder is 2. So answer is correct. Restoring division algorithm can be improved by avoiding need for restoring a after unsuccessful subtraction. So subtraction is said to be unsuccessful if the result is negative. In the restoring division algorithm, what we have done, we have subtracted divisor from the dividend. If it is positive, we determine the quotient as 1. If it is a negative, we determine quotient as 0, and we restored value of a. So in the non-restoring division algorithm, we avoid this step, restoring algorithm. So what we do? So we consider sequence of operations takes place after subtraction in preceding algorithm. A is positive. We are not restoring the value. So we are just using shift left and subtracting the a. So shift lefting a means a becomes 2a, and subtraction of a means 2a minus 1. If a is a negative, we have to restore in the previous algorithm. So to avoid the restoring, in the previous we are adding a with 2a. So in the next step we are shifting the value. So shifting value means this entire value becomes 2a plus 2m. So it becomes double. A plus m is becoming double. That means shift left operation results in 2a plus 2m. And we are subtracting m. We are subtracting m value. 2a plus 2m minus m. So which is equal to 2a plus m. So if a is positive, shift left and subtract. If a is negative, shift left and add m value. So this is non-restoring algorithm. These algorithms can be performed in two stages. In the first stage, for n number of steps, if a is 0, we shift left a and q 1 bit position and subtract m from a. If sign bit is 1, we shift left aq and add m. If sign bit is a, sign of a is 0, we set q naught quotient as 1. If sign bit is 1, quotient as 0. So this is of the second stage. After completing this for the n times, we have to again check the sign bit of a. If it is 1, we have to add m value, otherwise do nothing. After that, quotient will be in q and remainder will be in a. So let us see the flowchart of non-restoring division algorithm. So this is similar like restoring division algorithm, but if the sign bit is 1, means negative, we shift left aq and add m. If sign bit is 0, means that is a positive, we will subtract the value of a. Again, after this addition or subtraction, based on a sign bit of a, as if sign bit is negative, we take the quotient as 0. If the sign bit is positive, we take the quotient as 1. We take this quotient as 1 and we repeat this for n times. So, and if n is 0, we have to stop the loop, and as the final, if sign bit is 0, so nothing we can perform. If sign bit is 1, we have to add m value as a last step. So that is restoring for the last time. Understand an example of non-restoring division algorithm. 11 and divisor is 3, so its equivalent value is 0 1 0 0 1 1, and 0 and 3's equivalent is 0 0 0 1 1. Here the last bits are sign bits, and initially a is 5 zeros because number of bits in a dividend is 5, so we have taken a as 5 zeros, and as part of calculations we require minus m value. So we get this value by 2's complementing the m value. So 2's complement of 3 is 1 1 1 0 1. Now initially we keep all the values here. N value is 5, number of bits in quotient, and a is all zeros, q is 0 1 0 1 1. So we shift left a and q. We have shifted each bit position towards left. 1 0 1 1. We don't know what is the q naught value. Now check the value of a of n value is 0. If a of n value is 0, we have to subtract m from a. So m minus m value is 1 1 0 1. So subtraction of a from m means adding a with minus m value. Minus a is all zeros, minus m value is 1 1 1 0 1. So these two are added to get a as a minus m, 1 1 1 0 1. So 0 plus 1 1, 0 plus 0 0, 0 plus 1 1, 0 plus 1 1, 0 plus 1 1. So this is the result. So what is an value now? An value is 1. If an value is 1, q naught value should be 0. So this makes this value 0. Now decrement the value of n. So n becomes 4 now. So we have to repeat the same steps for the next cycle. So shift left a and q. So each bit is shifted leftwards, and this value we don't know. So we keep it as blank. Now a of n is 1. We have to add a with m. So m value is 0 0 0 1 1. This is to be added with a. 0 0 0 1 1 is added. 1 plus 1 1 0, 0 here, 1 here. 1 1 1 means 1 1, 1 here, 1 here. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 0 is 1. So now a becomes 1 1 1 1 0. Now the a of n value is 1, so which makes q naught value as 0. So if a is 1, q naught should become 0. So that is why we keep 0 in the q naught value and decrement the n value. N value become 3. Now we have to repeat the next stage. Shift left a and q. A and q are shifted towards left and we don't know what is q naught value. So now a of n is 1. For a of n is 1, we have to add a m value. M value is 0, 0, 0, 1, 1. 0, 0, 0, 1, 1 is added with this a. 0 plus 1, 1. 0 plus 1, 1. 1 plus 0, 1. 1 plus 0, 1. 1 plus 0, 1. Now a of n value is 1. This makes q naught value 0. If a is 1, q naught should be 0 and decrement the value of n. N becomes 2. So this is not 0, so we have to repeat the next cycle. Shift left a and q. So each bit of a and q are shifted towards left. Q naught value is not known. Now a of n value is 1, so we have to add m to the a. M value is 0, 0, 0, 1, 1. So this has to be added. 1 plus 1, 1, 0, 0 here, 1 here. 1 plus 1 plus 1 is 1, 1. 1 here, 1 here. 1 plus 1, 1, 0. And 1 plus 1, 1, 0. 0 here, 1 here. 1 plus 1, 1, 0. 0 here, 1 here. So this one is neglected. So now a of n value is 0. This makes qn value as 1. If a is 0, qn naught value should be 1. So this is 1. Now n value become 1. So this is not 0. We have to repeat the cycle. Shift left a and q. Shift left each bit position towards left. We don't know what is qn value. Now a of n value is 0. If a of n value is 0, we have to subtract m from a. Minus m value is 1, 1, 1, 0, 1. 1, 1, 1, 0, 1. This has to be added. 1 plus 1, 0, 1. 0 plus 0 plus 1, 1. 1 plus 1, 1, 0. 1 here, 0 here. 1, 0 plus 1 plus 1, 1, 0. 1 here, 0 here. 0 plus 1 plus 1, 1, 0. 0 here, 1 here. This can be neglected. So now a of n value is 0. If a of n value is 0, q naught should be 1. So this makes q naught value as 1 and decrement the n value. N value is 0. So n becomes 0. We have to stop the procedure. Now we can get the quotient at q. Q contains quotient 0, 0, 0, 1, 1 is a quotient. So which is equivalent to 3 and remainder is in a. 0, 0, 0, 1, 0, 0, 0, 1, 0. Its decimal equivalent is 2. So when you divide 11 with 3, we get the quotient as 3 and remainder as 2. So answer is correct. This is the non-restoring division algorithm.